Okay, hello everybody and welcome to the stream. So the topic for today is going to be a fun one. We are doing CVM hacks. So in some of the previous casts we've talked about digital assets and some smart contracts and some of the more economic side of what you can do with Convex and the kind of products and assets you can build. Today's going to focus a bit more on the sort of the nitty gritty of some of the magic that happens in the CVM and some of the programming tricks you can use to take advantage of these things. And I'm hoping we can sort of explore some of the more esoteric features that maybe we haven't discussed before or are sort of interesting from a programming perspective. Or just sort of quite neat things to know if you're developing code on Convex. So I've got about 10-15 different things to show off, and go through, do a bit of live coding and sort of explore some of these features. But as always, we've got the chat. If anyone wants to dig into a particular topic or sort of dive into something in more detail, then please do fire off a question. There's literally hundreds of things in the CVM, and we're never going to be able to show them all. But I wanted to go through a selection of sort of interesting things that maybe we haven't talked about before. So hopefully it'll be both entertaining and interesting. So let me just switch my screen here. And what we have here, as normal, we have the Convex REPL, so running on the Convex GUI on a small local Convex network. So I've got 3 peers running, and as usual, anything we type in here is just going to go through the REPL and get run as a transaction on the network. So if I can just type in a random number, execute that, it computes the number and it returns the result, which of course is the number itself. So this REPL concept, very much familiar to anyone who's been programming in Lisp or interactive tools such as IPython, or various tools now have been adopting this style of REPL-driven development, and it's a great way to test things out and sort of show off some of these features. So what to start with? I mean, first of all, I think it's just worth talking a little bit about code and data. So everything in Convex is data, and that includes code. So data can just be a number. It can be a list of numbers. I can have a vector. I can have a map with whatever objects I want, and you can nest these. You can do arbitrary structures, just creating whatever data you like, and that's the sort of the bread and butter, is processing, transforming data and doing useful things with it on a sort of secure platform. So when we actually want to execute code, so this is Lisp. So all you do is you put the function at the beginning. So let's say I want to do an addition, and then I put the arguments to my function after that. So 1, 2, and 3, and I close the brackets. I execute that, and I get the result 6. So that's performed a small computation on the CVM, and literally everything you can do on the CVM is following this model. You've got some kind of operation, and you've got some kind of arguments, parameters to that operation, and that includes doing transfers. It includes creating new digital assets. It includes even the programming tools all use this same model. But I think what's quite interesting is this code is actually also data. So if I do exactly the same thing, but I put a quote at the beginning, and I just do plus 1, 2, and 3, I get back just a list. It's a list with the brackets with a plus and a 1, 2, and a 3. Now it hasn't evaluated it. It's just kept it as data. Yeah, and this is a very important distinction. Yeah, if you execute code, it's going to evaluate it and come out with a result. But if you just have the code and you put a quote in front of the code, I can put whatever I like in here. I mean, this is garbage. This is not going to work as code, but it's just a list of symbols. Now, those symbols may or may not make sense. In this case, they probably wouldn't make sense, but you can have that as a list. So it's just a data structure, like any other data structure. And to show the power of this, it's important to think about, well, what does it mean to actually take data and execute it as code? And this is, I'm going to start off with the most powerful function, if you like, on the CVM, which is eval. Now what eval does is it takes some data and executes it as if it was code. So if I do eval and then I put in my list with my sum, now that list would not execute on its own, but if I put it through an eval, it will execute it, and that comes out with the answer 9. Now the point is, you can eval absolutely anything, any data. I can eval 67. That just evals to 67. I can eval a vector of numbers. That just is the vector. I can eval I can eval a symbol. So if I eval a symbol foo, which is undefined, it's going to give me an undeclared error because foo isn't defined in my current environment. So you can eval literally anything, and what it does is it just takes whatever that data is, it compiles that data as if it was code, and then tries to execute it as if it was code. And this is a very powerful feature that is particularly prominent in Lisp-like languages. Code is data, data is code, and you can swap between them as you do these things. And where it gets really powerful is you can use functions to construct data, and then you can use eval to execute that data as if it was code. So for example, if I was to make a list of, let's say the plus this symbol 1, 2, 3, that's going to give me a list of 1, 2, and 3. But I can also eval that. So I can create a code. I can create code to produce a data structure which represents code. Then I can eval it, and then I can just execute that. So eval is an extremely powerful function, and I just want to put a little caveat on eval. Is obviously you can have something like this. So it's a transfer. I'm going to transfer account number 14, 1 million convex coppers. That's not doing anything on its own. That's just a list saying transfer some coins to another account. However, if I eval that, so if I eval, let me just copy it. If I eval that, that's actually done a transfer. That's actually sent the coins to another account. So eval is dangerous. It's a double-edged sword. You can do literally anything that you can do as a user, you can do with eval, and that includes transferring digital assets. It includes sending funds to people. So the golden rule of eval is never use it on untrusted input. Yeah, if someone else passes you something and say, hey, please eval this, then the answer is probably you don't want to do that. Yeah, so eval should be used. It's a powerful feature, but should be used probably sparingly, and probably only when you trust the source of whatever the code is. And particularly powerful on Convex, of course, because this is an on-chain compiler, so you can compile and construct code in smart contracts. You can do it live. You can do it through transactions. Actors can construct code. You want to be sure that what you're evaling is safe and it's going to do what you want it to do. But this is very powerful for things like if you're creating a DAO or some kind of autonomous organization. You want to be able to have that execute arbitrary code. Once it gets approved, then eval is a powerful way of doing that. So that's the first little hack. And it's going to be important a bit later on as we come to, okay, well, how might you construct some interesting code? So I'll just clear this and go on to the next thing. So the Convex virtual machine is really running something called the lambda calculus, and this is the idea that everything in the machine is data, and some of that data is code, and some of that code can be functions. So we have first-class functions on the CVM. So a function is something that'll take inputs, do some operations, produce some outputs, and these are first-class in the CVM. So you can pass functions around as parameters to other functions. So the whole of functional programming therefore becomes possible, and indeed quite quite normal on the CVM to use functional programming techniques. I'm just going to demo a couple of things. So I'm just going to create a simple function. So we use defen to create a function. Let's say we want a function to say if an integer is even or not. So we're going to call it even, and we need to say what arguments even is going to take. So in this case, we're just going to have an x, some unknown parameter is going to come into our function, and then we provide whatever we want that function to do. So in this case, we want to test if it's even. How do we test if it's even? Well, what we can do is we can see if we do a modulo division, if we divide x by 2 and the modulo of that is 0, then we are going to be an even number. And that's all it takes to define a function on the CVM. And what that's going to do is, because it's a defen, it's going to create the function even in the environment of this account. So if I type even now, even is now defined, and that's actually the the compiled representation of the function. Notice it's replaced the x in here with a %0, which just means the the first argument on the stack. But that's the compiled representation of this even function. If we want to use it, well, as always in Lisp, we just put that as the first thing in the list. We say is 12 even, and we get back a true. So that's good. That works. Is 17 even? We get back a false. So okay, that looks like it's plausibly a working function. Notice that we don't need to define it. Yeah, if I wanted to ask the question if this number is even, I could just do an anonymous function. So if you do a fun without the define part, just to have a fun, I can just say it's a fun of x, and it's going to do the same thing. It's going to be equals mod x2 0. All I've done is inline defined the function. Yeah, so you don't actually have to define it. You can just put it in like that. It's usually for readability. It's better to define it and give it a good name. But you can absolutely do this, and this works in exactly the same way as a defined function. So that's just a function. But where functional programming gets powerful is you can then combine that with other functions and pass functions as arguments to other functions. So one of the classic functional programming lambda calculus constructs is the map. So what map is going to do is it's going to take a function. In this case, we're going to say even, and then we can give it a data structure, a list of things. So let's give it some numbers. Execute that, and what it's going to do is it's going to run the even function on each element of the data structure. So if I execute that, I get a vector back, which is false, true, false, true, false, true. So that looks like it's working, at least for those the first few numbers at least. So that's an example of a higher order function. So map is a function that takes a function as an argument, and you can put whatever function in you want. Yeah. So if I can do the same thing with I can map increment over the same numbers and execute that, and it's just going to do inc on each of the numbers. So I get 2, 3, 4, 5, 6, 7. So any function will work as an argument to map. You can do what you like. So for example, I've got a question: could I take a function that was a 512-bit crypto algorithm for a greater level of security? Yeah, I mean you could create functions to do whatever you want. I mean the cryptography stuff, I mean typically you don't do it on the CVM. Typically the cryptography is done off the CVM so that you can keep your private keys and things private. But yes, you absolutely can do crypto algorithms on the CVM and wrap them up in functions. You're probably more likely to be doing verification on the CVM rather than the underlying thing. So for example, there's a hash function. Is that a valid? There's a hash function which will hash get me the hash of any input. So let's say that's some kind of secret. I can say I'm not going to let my smart contract do anything unless this secret is revealed, and someone can provide an input that hashes to this value. So you're going to verify that someone has that particular key, which is going to unlock the hash. So if you're going to do something like a hash time locked contract or something like that, you'd use hash functions to make that work. 256 bits should be fine for cryptographic hashes for the foreseeable future. But yeah, good question. These functions can be absolutely anything. They can be crypto. They can be crypto stuff, whatever you like. Map is, as I say, one example of a high order function. So another example is filter. So filter, I'm going to filter even. Oh, filter, no question mark. I'm going to filter even some list of numbers. And if I do that, it's going to filter the ones that meet the requirements. If I do that, I get 2, 4, and 6. So it's just filtering the list and giving you some subset. So this might be useful, for example, if you're checking a list of allowable options or something like that. You want to filter out things that aren't valid before you process them. Filter's a good one, and then there's another one that is quite good, which is reduce. Reduce is just going to take some function, let's say plus is an example. Plus is again just a function. I can reduce plus over some list of things. I mean, in this case, I could use plus directly, but just to demonstrate it, I can do that, and it's going to basically do it as if plus was inserted between each of the elements in that list. So that's an example of another high order function that's quite useful. And of course, you can combine these. Yes, if I can reduce plus and filter even, I just want to add together the even numbers. Then it's just going to add together. It's going to filter first, and then it's going to add them together. So you can combine these in lots of different ways to create the computation that you want. What's the advantage? Well, I didn't have to write a loop. Yeah. So instead of writing a loop, you can just do these quick one-liners that do actually quite powerful data transformations. And this is actually good for security as well, because you avoid things like off by one errors on loop indexes and things like that. It's easy to make mistakes with loop indexes. So using these kind of high order functions is often a powerful way to write more robust code. And obviously, if you use functional programming languages like Clojure or Haskell, you're likely to be very familiar these kind of techniques. So let's look at something slightly different. We've done a bit of functional programming. A very common requirement is guards. So you want to protect yourself from some scenario that might be a problem. You want to abort an operation, for example, if something's not working. So there's this function in Convex Core called when. Yeah. Now what you do is you can put in a condition. Say when something is true, then do something else. And the very common pattern is, like, let's say I want, whenever my sequence number, so the sequence number is the number that increases every transaction. Each transaction increases the sequence number. When my sequence number is even, I want to fail. Going to do this. And if I execute that, I don't know if it's going to fail or not, because I don't know my sequence number at the moment. Okay, so that's failed because my sequence number was even. But if I do it again, passes. It just, you know, it fell through and returned nil at the end. If I do it again, it's failing. Do it again, it works. So when is creating a sort of guard that when the condition is true is letting you do something special. Typically in Convex code, you would want to do this to validate inputs. Yeah, check that your inputs are valid, or that the person has sufficient balance or has sufficient utility tokens to do a certain operation. You want to stop the operation early if some condition isn't satisfied. So it's a very common pattern. You'll see this in a lot of the digital asset code on Convex. If you want to do, you know, more complicated expressions, you can also use or. So or is a bit like when, except you can have multiple things. So if I have an even sequence or an even this is never going to pass. But I can put in as many conditions as I want. Even, balance, then fail. Yeah, so that returned true, because what OR does is it returns the first one that evaluates to true. So even sequence might have been true, even 19 definitely wasn't true, even balance might have been true. One of those came to true, so it didn't hit the fail operation at the end. So this is again quite a common pattern. You'll see these sort of these ORs testing for possibly multiple conditions and then failing. But otherwise it works a bit like when. Now the important thing to note is this fail here doesn't get executed in this expression. If that got executed, the whole thing would fail right at the beginning, yeah, because it's if this was a regular function, what it does is it would compute all the arguments and pass the arguments to the function, and therefore it would fail while computing this argument before OR even got called. So very important to note that OR is not a function. It's actually a macro. So there's some code inside. This is actually a macro which is transforming the guard into an expression that only executes this fail thing if one of the earlier expressions doesn't happen. So what are these things called macros? So it's probably familiar to people who've used Lisp before, but many languages don't have a powerful macro system. So worth diving a bit into this. So we have def macro. So let's say I want to create a macro called sum, and all I'm doing is I'm providing some code. So remember when we put an eval inside some, we did an eval earlier. A macro is just something which produces some code to represent according to the rule, the pattern that the macro defines. So in this case, I've just, you know, create a sum macro which has got this plus 1, 2, 3, 4. So that's now a macro defined in my environment. So if I do sum, what it does is it replaces that sum with the code that the macro defines and executes it. Now, if I want to see macros similar to spreadsheets, not quite actually. Good question. Macro and spreadsheets are really just a program. It's like a memory of a program that you want to run. What a macro is in Lisp is really a function that creates code. Yeah. So if I do expand on sum, for example, sum is just a macro. Oops. Okay, so that didn't work. So I'm going to put a quote in there. Yeah. So if I expand this code, so the code that is just sum in a list, it produces this code. So what happens, in fact, is all the macros get expanded out to create some larger code, and then that code is what get executed. But if you use the expand function, you can just expand it and see what would have come out if you at the end of the expansion without actually executing it. Now the important thing about macros, of course, is macros can have whatever code in that you like in the macro expansion, and because it's not yet been executed, you don't have to actually have to run it. So you can have things like fail that would otherwise stop execution. You can build the code to do whatever you want. So let's give a slightly more interesting example. So let's say we want an unless macro. Yeah. So I want a macro that's going to say unless. Let's say unless my balance is low, I want to send a donation to someone else. Transfer some coins to someone else. Yeah. So unless isn't defined, but that's what we want to do. We want to create a new language construct that has this unless logic. So it's a bit like when, but it's almost like the inverse of when. So how would we do that? Well, again, it's just a macro. So we do a macro, def macro unless. We're going to have two things in our macro. We're going to have a test and an action. So the action is going to be the second argument, the test is going to be the first argument. And let's just space it out a bit so we can see that. So we want to produce some code. So what expresses the logic of unless? Well, it's kind of an if statement, isn't it? So it's a if, but it's unless. It's not if, it's unless. So we need to reverse the test. So we do a not, if not, if not the test, then I want to do the action. Yeah. So if the test is not true, then I want to do the action. Now, notice this little tilde here. Yeah. This is because I want to substitute. This pattern here is code, but I want to insert in the code at that point the code that comes in as test or action. So it looks a little bit different from a function, but it's really just a function that produces code. And this backtick is a special kind of quotation mark that allows you to use these unquotes, these inside the macro. So if I define unless like that, again I've got a macro, and now our unless function should be working. So yeah, that's transferring 100 each time, every time I execute that. So what happens if you expand unless? So let me just copy this. If I was to write that code and expand it, you can see it's expanded to this expression here. So you can see that it's inserted in my code, my transfer code, and my test with the not in. And notice it's turned the if into cond. So it's a cond statement. Now why is that? Well, that's actually because if itself is a macro. So you can have macros inside macros, perfectly acceptable. And what expand is doing is expanding it the unless the first time, producing this if expression, and then because if is itself a macro, it's then expanding it again and turning it into this conditional expression. If you only want to expand once, let's say you want to see just your expansion of your macro, and you don't want all the sub macros to be expanded, that's fine. We have expand one, so that's expand just once, and you can see that then produces exactly the pattern that we defined in this macro here. So the if statement, which then of course needs another expansion if you're going to get to the cond. But expand one is very useful if you're debugging a macro and you want to just see how the top level macro expands. So bit of magic. You can do incredibly powerful things with macros, and what I really like about macros is you can use it to define your own language. So if you have a custom set of commands or rules or language constructs that you want to create, like unless, I've just extended my language. Yeah, in most languages you couldn't create something like an unless, because as I say, it won't work as a function. It's transforming code rather than running as a function. So you can use it to define your own language. Yeah, you define a few macros, and then you can use the macros to express your code in a more natural way if you've got a domain-specific language or something like that. So powerful feature. You know, obviously very commonly used in Lisp. Obviously, Convex Lisp obviously has it as well. I would say that macros are a little bit black magic. You don't necessarily want to use them unless you know you need them. Yeah, so probably it's better to use a function in most cases until you've convinced yourself that actually, because I'm doing something like this unless function needs a macro, because I'm doing something that alters the evaluation order, I actually need a macro to do that because it won't work as a regular function. So that's when you start reaching for macros if you need to do something a bit special in the language you're defining. Okay, so now that's all fairly standard Lisp stuff. Let's go into something a bit more Convex specific. So we do have memory accounting in Convex, and every account gets a memory balance, a memory allowance. So if I just do memory, and this is quite common by the way, Convex has a lot of these little special words that access something in the CVM, and in this case the memory is how much memory allowance I've got. And you see I've got this 9999581. That's how many bytes of memory allowance this account has, which is actually quite a lot. You know, that's what 10 megabytes of memory allowance sitting around unused. Now, what happens with memory is whenever something happens in the CVM, this value basically is getting updated, and we're seeing some changes. So if I define something, let's say define A to be hello world. So I've just defined A to be a string. Execute that, and then if I do memory again, you'll see the memory balance has gone down slightly. It's gone down by what, 16 bytes. So that hello world data plus the data to store this new symbol in the environment has taken 16 bytes of memory. So whenever you do a def or define something in the environment, you might alter the size of the CVM state. So it's going to change the size of the overall CVM state. And if you increase the size of the CVM state, it's going to reduce your memory allowance. And if you get down to 0, it'll actually buy more memory allowance. You have to buy more in order to be able to execute that operation. So if you want the memory allowance back and you decided I don't need that, a very useful CVM hack is undef, which is undefine. So this does the reverse of defining something. I just undef A, and if I do memory again, you see I got my full allowance back again. So if you clean up memory after yourself, you get all of the memory allowance back. So question is buy memory going to be automatic? Yes, it is 100% automatic. If you need more memory and you define things, it won't fail. It'll just try and buy more memory. It'll only fail if you can't afford the additional memory. Yeah. So you don't have to think about memory if you don't want to. Yeah, because first of all it will use your memory allowance. So here I've got quite a lot of memory allowance, so it's going to use that first. And it's only if that memory allowance gets to 0 then it buys it from the memory pool, which is like an automated market maker. But great question, like you know, do you want to buy memory at a certain time for a certain price. Yeah, so let's and that's what this is about. This is let's try out let's write a memory trading system. This should be fun. So what the actual CVM command to set your memory allowance is called set memory, and I can set my memory to be whatever number I want. So if I set memory to 1000, it said this big negative number. So actually I got a refund from the memory pool. Yeah, that's extra Convex coins deposited into my account for selling the memory back to the memory pool, because I was originally at like 10 million or whatever, so I got a decent sized refund. If I do memory now, it's going to be approximately 1000. In this case 1002. Why isn't it exactly 1000? Well, I did set the memory to 1000, but I got a slight refund at the end of that transaction. Yeah. So you can get a refund at the end of the transaction, which means that that you get slightly more than you sold down to. Why is it 2 bytes? It's fact because I actually got a refund because I made my memory allowance smaller, which means that my account actually uses less bytes to represent the number of the memory allowance. So I actually made the CVM state smaller, so I got this extra 2 refund. But that's effectively what you can do to do that. If I want to increase my memory again, so I want to go back up to 10 million, you see I then pay, you know, approximately equal price for going back up again. I think I made money. Oh, that's a different number. Yeah, that's a different number. But you know, you can see that the amount of memory price that I paid for that memory. So if I wanted to, okay, that's not. This is a bit of extra calculation. So let's define a function. So let's define a function buy memory. I want to buy a certain amount of memory, x, and what I want to do is I want to set memory to, well, I want to add to my current memory allowance. So plus memory x. That should work, I think. Yeah. So if I do buy memory 100, it's going to buy an extra 100 bytes of memory, and I can keep doing that. And it's giving me some extra memory each time I execute. If I want to see the memory price, there's a memory price special which returns what the current price is. Actually gives you it as a decimal because it's a automated market maker, and it gives you the precise gradient of the price curve at that price. So you can see this this memory price that I'm paying, and every time I buy memory, it should be very slightly increasing the memory price. Yeah, it's, you know, a few decimals down here are changing. So you very slightly change the memory price if you as you buy memory. Now, of course, you asked a great question, like, are you comfortable with the price that you're paying? So you might be happy with the current memory price, but the price might change in between when you check the price and when you execute your transaction. I mean, you could even get potentially front run by someone, yeah, pumping up the price of memory as you buy and then dumping it once you've paid some extortionate amount. So if you're doing a lot of memory trading, I mean, it wouldn't matter if you're doing small trades, but if you're doing large memory trades, then you might actually want to guarantee a price, lock in and guarantee a price. Now, this is tricky, yeah, because, you know, something might happen. It's a decentralized system. Things happening all the time. Price can change. Yeah. So how do you guarantee a particular price? Well, let's change our buy memory function. So let's go back up. Yep, that's the buy memory function. So let's customize this a bit. So we're still going to want to set the memory if we buy, but let's do a let. So let is going to let me create some local variables within this function. So what I'll do is I'll say So the amount I want to set it to is this thing here. This is going to be my new memory amount if I do the buy. Yeah, I'm not actually buying it. I'm just computing the new amount because we're going to need that amount. Now I want to know how much that's going to cost me. So I'm going to say the cost. How do I get the cost? Well, this is an absolutely magic CVM hack. You can do a query. Now what the query does is it executes some code but doesn't actually change the CVM state. So anything you do in a query can't change the CVM state. You can do anything you like, but it's not going to actually happen. Yeah. So I'm going to put my set memory amount inside the query. So it's going to do the buy of the memory, but it's doing it in a query, so the purchase won't actually happen. Yeah. Now, what I want to do then is when, so I'm using the when function that we used earlier. When so it's I'm looking at the cost, yeah. So when divided by the cost X, so I'm buying a quantity of X and the cost, some cost of it. So that's going to be the memory price I paid. And let's say I would put in another argument, max price. When cost of X exceeds max price, I am going to fail. Too expensive. Now, if that passes, then the cost must be less than the max price, or at least equal to the max price. Yeah. So I'm then actually going to do my set memory to amount. Yeah. So I'm actually going to execute the trade. That looks about right. Okay, so we now have a buy memory. So if I do buy memory 100 and I'm willing to pay up to 900. Okay, I think that worked. I think I bought some extra memory. Where are we? Yeah, got 1,317,000. Do that again. Yeah, I'm buying 100 memory each time. So that looks good. But if I say buy memory, but my max price is going to be 200. Okay, failed. Too expensive. Yeah. Now, so you can put in these guards and a query to do the test, see whether the thing you want happens as you expect it to happen, and fail if that isn't true. And I think we find that the memory hasn't actually changed. Yeah. So I didn't actually. It worked out that the trade was too expensive, but because I did the actual trade in a query the first time, it hasn't actually bought any memory. Yeah. So you can use this to ensure that you get a certain price, which is very powerful if you're worried about slippage on a DEX. So you can do this with Taurus on the DEX. You can set a maximum price for a trade and make sure it happens. Now, why is this safe? It is safe because I defined all of this in a single function, and I'm executing that function in a single transaction. So the entire transaction is atomic. Yeah, this is where atomic transactions are extremely important. Because it's atomic, nothing else can happen in between that would change the price of the memory other than what I'm doing. Yeah, no one else's transaction can come in between me checking the price and me executing the trade. So that's where atomic operations really give you this extra degree of protection for controlling access and these kind of things. So very powerful trick. Use a query to check whether the thing that you want to do works or not before you do it. But cool, yeah. Thanks for giving me that example. It's a great one to look at. Let's let's give another example. Oh, you can query as. So you can query as someone else. Yeah. So let's say I create a new account. I'm going to find Bob. I'm going to create an account with. Let's just use my own key. Doesn't really matter for this. So I'm creating a new account. I've created account number 57. Has Bob got any Convex coins? No, he has 0 Convex coins at the moment. If I transfer Bob, let's give him 10,000. Right, so Bob now has 10,000 coins. So I can't do anything with those 10,000 coins. Yeah, it's Bob's coins. I can't access them, and I could, because I know his key. I could go and sign a transaction on Bob's account. But let's say I didn't know his key, and just sitting in the account. But I was still interested in what can Bob do with his 10,000? Yeah, I can do query as. Yeah, so I can do query as Bob, and then I can just say I'd like Bob. What would happen if Bob executed the following code? So if Bob executed the following code, transfer, let's say to 13, and let's say he tries to transfer 20,000. So I'm basically asking the CVM to run this code as if Bob was running it, and what would the result be? And I get a funds error. Yeah, Bob can't execute that because he hasn't got 20,000 coins in his account. Yeah, but I can also say, okay, if he was to transfer just, let's say, 300 coins, that would work. Yeah, so you could use query as to see what would happen if someone else on the system executed some code. Now notice that because it was a query as, and queries never get actually executed, if I go back to Bob's balance, he's still got 10,000. The 300 didn't get transferred. It was purely a query context. So quite a neat little trick. You can use this to see what would happen if someone else did something, and it can be yourself. Yeah, I can say, what would happen if my own address. It would transfer 3,000 if I tried to transfer some ridiculous amount. Oops, that's too big for a transfer. Maybe this is going to work. Too big again. Too big again. I'm going to get it right shortly. There, funds. Yeah, I haven't got that much. Yeah, so I'm querying as myself, so again I'm safe. I can't actually do anything. I can't actually do anything that would actually harm my account. I would get the same if I just. Wrapped that in a query. Oops. Yeah, oops. Yeah, same error, insufficient funds. But of course, this is going via query as. This is just a transfer within a query. So a little bit different way of doing the same thing effectively. So that's quite a powerful tool, and you can use that to do some more programmatic things. So you can even use query as with accounts that nobody can use. So I can query as account number 8. So account number 8 is the Convex core library. So this is all of the core functions that are available in Convex. So if I was account number 8, which nobody is account number 8, what would happen if I ask for the keys in my current environment, and I get this vector, which is the symbols that are defined in the core environment. So you can see all the stuff that actually makes Convex work in here. So you've got for example, what have we got? A bunch of functions that we've been using. So you've got create account, you've got juice limit, you've got balance, you've got transfer. Yeah, so all the functions in the Convex core library are basically stored in account number 8. But that is basically the things that I would, if I ran keys environment as account 8, I would get that result. If I just do keys env myself, all I have is these things that I defined earlier in this demo. So even, by memory, unless, sum, and bob. Yeah. So that's my environment is a lot smaller than the core environment. Yeah, neat little trick if you want to play around with that. There's also a val as. So a val as, and I have covered it in the previous thing, but a val as is just like query as, except it actually tries to execute it. So if I do a val as 8. Doesn't really matter what I try and eval. Let's say here's something. This is going to try and execute it using the security context of account number 8, and it doesn't like that. Yeah. Trust, I cannot control the address, so there's no controller set on account number 8. No one's a controller for account number 8. It's the core library. So eval as fails because I can't execute any code in that account. But if I did it on an account that I did control, then that would work. So how do I? Can I demo it? Yeah, okay, let's do it. Let's show one more neat little feature. I'll clear this. So deploy. The deploy function is what actually creates new accounts. Yeah. What this is going to do is it's going to create a new account, and it will execute precisely the code that I give it. So this is exactly like a val. So what deploy does, and this is how it all starts to fit together. Deploy creates a new account and then evals some code in that account. Yeah, using that account security context. So if I just do deploy nil, I get a new account, but there's no code in it. There's no that's a dead account. It's unusable. No one can access it. But if I was to deploy the account and say set controller to myself, and I am account number 12 at the moment. That's created account number 59. So I can now do eval as account number 12. I can execute some arbitrary code, whatever I like, as account number 12, and that works. If I transfer that account some coins, 59,000 coins. Oh, I messed that up. It hasn't got a received coin. Okay, I'll do a different account. 1 sec. That's a protection, actually. That's a security check on set controller. So I'm going to have a controller, but I'm also going to give it a key because it thinks it's an actor, and actors don't receive coins unless they're set up to receive coins. So I'm just going to set the controller to be 12, but I'm also going to set its key, so it looks like a user account, to be my own key. Again, this because I'm quoting this. I use this little tilde, which means that I want to insert my own key in this place in the code that I'm executing. That's going to create account number 60. I should be able to transfer to 60 OK, because that looks like a user account because it's got a key set. Okay, so that worked. And now if I do balance of account number 60, they got 1,000. But because I'm the controller of that account, if I eval as account number 60, and I transfer, again I'm going to quote this because it's going to eval it, transfer back to myself 700 refund, execute that, looks like it's transferred 700, and you can see if I do balance 60, it's got 300 left. So that actually executed that within the context of that account. So difference between a val as and query as is query, there's no trust controls. You can query as anyone you want, but you don't actually affect the CVM state, so you can't do anything harmful to that account. Whereas with a val as, you're trying to take control of the account in order to run some code, and then you absolutely have to be the controller of that account, or set up so that you're on an access control list or something, so that you've got the power to execute that. So this is some quite cool CVM hacks that you can use if you're developing, but you can also use it to build more sophisticated smart contracts that maybe have multiple smart contracts interacting with each other, or generating new smart contracts, or generating new accounts for users of your app or something like that. Yeah, you're going to be doing something like this deploy. Like if you're a mobile app and you wanted to create new accounts with a controller so you can get account recovery, then you would probably want to do some deploy, something like this. So you'd be setting up the user's key, whatever the key the user has in their app, public key, but you also want to set the controller to be some governance account or some recovery account that's letting you have the access to do account recovery. So you can basically do whatever you want in deploy. Whatever code you want to do to set up the new account, you can do in here. Basically, no limit. And that's actually basically what happens with all of the Convex main actors. They're just being deployed with some code which implements an automated market maker or something like that. I think we've probably got time for one more little fun thing. So this is an interesting one. So you can create recursions. Functions can call themselves in Convex, but this creates some interesting problems. So let's say I create a function called deep, and what this function is going to do is going to call itself. Yeah. So what I'm doing is I'm setting up some infinite recursion where this deep function calls itself, and it's going to be calling itself inside itself indefinitely. If I execute that, I've just defined a function. Yeah, nothing happens. Yeah. If I run it, what happens is I get this horrible stack trace. What I've done is I've effectively exceeded the maximum depth allowed in the CVM. Quite a lot of stuff here. Yeah. So it's invalid depth 25257. So the CVM for safety implements a maximum recursion depth. It's pretty deep. I mean, you're very unlikely to recur more than 200 elements deep, but if you do, you've almost certainly done something wrong. Yeah. So what it does is it fails with the depth limit. Again, this is protecting you to some extent. Yeah, because if you didn't fail with the depth, it would burn your entire juice allowance. Yeah, you'd spend your entire maximum transaction cost just getting the CVM to spin on infinite depth, which would not be useful, and waste your funds from a simple mistake. So we don't really want to do that. But let's say you're doing something that does have quite deep recursion. Yeah. What you want is to be able to do recursion, but without accumulating unlimited depth. So Convex has this thing called tail calls. So tail calls in software is where you do a call at the end of a function, and you don't add extra depth to the recursion stack. Yeah. You don't want to burn all your juice. It's not good. Yeah. So there's actually a juice limit. It's one of these specials. So currently it's set at 10 million convex coppers. So if you try and burn more than that amount, it will fail the transaction. So there is actually a limit that it enforces, which means that you're not going to bankrupt yourself by blowing the juice limit. But it will be an expensive transaction, and it won't do anything because it'll fail. So you definitely don't want to be doing hitting a juice limit if you can possibly avoid it. Yes, there is a feature for setting something else, although I think that default is fairly sensible default, so you probably don't want to change it. It's like small enough that you're not going to bankrupt yourself, but it's big enough that you can do anything reasonable. Yeah, so it's quite a good default. But let's say I deliberately want to blow my juice limit. Yeah, I can't do it with the deep recursion because the stack depth is going to is do it. But let's call it burn. So what burn is going to do is it's going to be a function. We can't do infinite recursion because we know that we get protected from infinite recursion. But we can do recur. And what recur is going to do is it's like a jump. It's like almost like a go to it. It's going to go back to the enclosing function in this case. Now what this is going to do is it is going to create an infinite loop. So I am going to burn my entire juice limit. So this should fail with a juice error if we run it. So I do burn out of juice. Yeah. So it's basically set up an infinite loop. It executed a loop until your 10 million convex coppers was burnt, and then it failed. So that's what happens if you try and do something excessively complex, or most likely an infinite loop. You will get these juice exceptions. So just handy to know. There are a few very special circumstances, like let's say you are writing something that's going to be a loop, then you do want to use recur so that you avoid accumulating stack depth. So you don't really want to what's a good example? I think Fibonacci. Is Fibonacci a good one? Fib. There's a recursive way of doing Fibonacci. N. Recur. And what we're going to do is factorial is probably the easiest. Factorial is we're going to recur times ac n and dec n, and we're going to do when n is greater than 1. So this isn't going to infinitely recur. Okay, and let's just show off another little feature. You can have multiple arities. So I'm just going to put in an extra arity. So if I provide 2 arguments, it's going to do that. If I provide simply 1 argument, it's going to again recur, but it's going to recur with 1 and n. I think that's probably right. So if I do factorial of 10, oops, that's not worked. Oh yes, so if n is greater than 1, then recur like that. Otherwise, just return our accumulated amount. We need to actually return a value. That'll be helpful. Okay, there we are, and that's, I think, the factorial of 10. So this is a factorial function, so it's producing 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 10, etc. If I do a big number, something that would blow, this would blow up the depth if this was, you wrote a recursive factorial. There you are, there's a factorial of 300. Yeah, so as you can see, it's quite a big number, and that would be, if you did 300 loops in sort of recursion, you'd blow the stack depth. So yeah, so also nice showing off some big integers there. Again, useful. So that this recur is actually when you actually really want to do a loop is a very good way of doing it, and it's also very juice efficient. So it's like a go-to. It's a very cheap operation. So loop and recur, or a function with recur, is a good way of building functions that operate on, you know, need to do many iterations. Having said that, I would always say that when you're doing code on the CVM, if it looks like you're doing a big recursion or a big loop, you're probably doing something a bit wrong. You probably shouldn't be trying to process very large data structures sequentially in a single transaction, because that's probably a bad idea. You're probably going to incur quite high transaction costs as the data structure gets bigger. So, and also you may be possibly leaving yourself open to denial of service attacks. Yeah, if someone sends you like a really big input, well, you know what happens. So worth being careful if you're ever doing a lot of iteration, just to be sure that you're not doing something that's exploitable, or is going to shoot yourself in the foot for some reason. Okay, so I think we've sort of run out of time, but hopefully that was interesting. Shown a few of the sort of cool little programming tricks on the CVM, and thanks for some great ideas. Yeah, we built a little memory trading system, which was a nice example of how you use some of these tools. And there's a lot more in the CVM, a lot more powerful features of various different types. So as always, if you want to ask on some of the more detailed stuff, then you do drop by the Discord, and happy to go into some depth on all the different things you can do there as well. Well, thanks all for joining, and hopefully see you all again soon. Take care. Bye for now.